Welcome back, and this time we're going to look at titration curves in a little bit more detail, look at a few more calculations and introduce the idea of buffers. So as we've looked at before, titration curves essentially plot the change in pH that occurred during a titration. The initial starting point of the curve tells us what we start with in the flask, be it a strong acid, strong base or weak base, and its relative strength. So we can see here with these two on the left here, we're starting with a very high pH, so this will be a strong base, where the pH is starting up around 14. And then here we have a weak base as our starting point. As it drops, we can see that it finishes down under a pH, around a pH of 1, so this means it is being titrated with a strong acid. This weak base is being titrated with a weak acid. We have a strong base here that is being titrated with a weak acid. And then we have a strong base and a strong acid in this one. And as we can see, thanks to the idea of salt hydrolysis that we saw last time, the equivalence point, which is half this vertical line, is at 7 for the strong base, strong acid. For the weak base, strong acid, we see an equivalence point closer to 4. Then strong base, weak acid, our equivalence point is closer to 9. And then with a weak base and a weak acid, there is no clear equivalence point. We don't have a very vertical line. And we've talked about this before, so hopefully that's quite familiar. When we come to talking about the other regions of the curve, we will see what we call the buffer region of a titration curve. Now, buffers are substances that resist a change in pH. So we can add acid to a buffer and it won't change pH much, or we can add base to a buffer and it doesn't change pH much. This is because we have both the acid and its conjugate base salt present. So if you think about it in terms of we have our acid plus its conjugate base, so the A minus, present in solution. And this sets up an equilibrium system. So if we add in H+, the conjugate base can accept the H+, driving the equilibrium system back this way, and HA will ionize. Okay, or if we add base, then we will change the equilibrium position. Will remove H+ here, forcing the equilibrium back. So because this is an equilibrium position, if we have a sufficient amount of both the acid and its conjugate base, then it can absorb slight changes in OH- or H+ being added to the system by shifting the equilibrium. So by definition, we say that we get a buffer region or a buffering system when half the base has been added, i.e. the acid has been half neutralized. So if we were to take 100 milliliters of ethanoic acid and treat it with 50 mils of sodium hydroxide, you would end up with half the ethanoic acid being neutralized, assuming they were the same concentration. So once you've done that, once you've neutralized half the solution, you have a buffering solution. So where the concentration of the acid equals the concentration of the salt, we find the relationship that the pH is equal to the pKa. And if an acid is being added to a base, the base concentration is equal to the salt concentration, the pOH is equal to the pKb. And we see this in titration curves by looking at these here. These regions that we get, these sort of flatter regions that we get on the side of the equivalence point, before the equivalence point, from the start of titration, these flatter regions, these are the buffering regions. And at half the equivalence point, we find the pKa and the pH are equal. So in a buffer region, the pH will be equal to the pKa at half the equivalence point. So in this case, 50 ml of KOH was added into the solution. So this is the volume required at the equivalence point. And then at half that, so at 25, we can determine the pKa of the system by at the pH point. So if we're starting with a base, the buffer region is going to be the flatter region prior to the curve, just before the equivalence point. And again, the pH at half the equivalence point would be equal to the pKb of the base. So as we said before, this is just our titration curves and determining the equivalence point for each, remembering that for a strong, the equivalence point will be 7. For a strong, weak, the equivalence point moves towards the stronger of the two options. So for a strong base, weak acid, it moves towards the base, making a pH of 9 for the equivalence point. And for a weak base, strong acid, it moves below 7, moving towards the stronger, with a pH of around 4 to 5. So there are a number of features that you have to be able to identify in the pH curve, this being the initial pH of the solution, the buffer region, which is the flat region prior to the equivalence point, the equivalence point, which is halfway between the vertical line we see on the graph, the pH of the equivalence point, the final pH, and the general shape to be able to tell if it is a strong and weak or a weak-weak combination. So what we can do is actually calculate pH during the titration of a strong acid with a strong alkali. So to do this, we can determine the initial pH. So these are referring to the alkali that was added. Okay, so the base being added here because we're starting with a strong acid. So 0.1 is going to be at pH 1. So H plus concentration is 1 times 10 to the negative pH. So then add that into our pH is equal to negative log of base 10, the concentration of H3O plus. That's the one that we've rearranged to work out the H plus concentration. Then at 25 centimeters cubed, which is half our equivalence point, so in the buffering region here, we can now look at the initial mole of the acid multiplied by this volume here, okay, gives us the total mole of the acid. The mole of the base added is this. So this is the full amount from here. This is the total mole of the base added at 25 milliliters from the initial concentration of the base. Then we see here that we have the initial mole minus the mole at the point we're looking at, means this much mole of acid is left. Total volume is the initial volume plus the volume that has been delivered. So we can now work out the concentration of H3O plus and work out the pH. At the equivalence point, we know all of the acid has been neutralized by the alkali to give a sodium chloride solution because this is strong, so the pH will be 7. And then after the titration, after the equivalence point at 0.4, we have excess base. So we can determine the amount of base that is left and then determine the pH from there. Titration curves for polyprotic acids you just have to be able to recognize, and these essentially will have multiple equivalence points for each stage of the ionization. The first one will be the strongest, the first ionization. So for this is for the H3PO4, so this one will be at the formation of the H2PO4 ion. And then the second will be at the loss of the second one, so HPO4 2-, and then the third will be at the formation of a PO4 3- ion. And you can see with each one it's getting more basic as the nature of the anion changes. As we've mentioned before, being able to determine the pH of the equivalence point affects what indicator that we would use in a titration. Indicators change color depending on the H3O plus concentration in solution. They are weak acids, with their acid form being one color and their conjugate base being another color. So because they're in weak acids, they are in this equilibrium system here, where we have the protonated indicator losing the proton and forming the conjugate base being a second color. So the different indicators change color in different pH ranges, as we've seen before. We can do a lot to determine endpoints in this case by looking at the equilibrium system of the indicator. So the endpoint of the reaction is at which the indicator will change color, remembering the equivalence point is where they're stoichiometrically equivalent, but the endpoint is where the indicator changes color. pH of the endpoint can be calculated using the pKa of the indicator, okay, which is the PkIn is how we refer to this. It's just the pKa of the indicator. The indicators are weak acids, so we can write the dissociation constant for K indicator with the H plus ion minus over HIN, leaving out water as we have in the past. So to convert the P to pKa, we need to take the negative log to base 10 of the K-in. Okay, so essentially this means that we have the PkIn is going to be equal to the pH as minus log 10 of this in over H in concentration. So what we do is we can derive this equation here, which is that the pH is equal to the PkIn plus the log to base 10 of the concentration of the indicator over the concentration of the protonated indicator. This is the Henderson equation, and the color of the indicator is going to change when the indicator, ion minus the base, is equal to the HIN concentration. So when we are at this point, okay, so where the color starts to change, the relationship simply becomes pKin is equal to pH. So the pH of the equivalence point is going to be the pK equal to the pK indicator. So this means we're going to have the indicators changing color at PkIn. This, you'll have about a plus or minus 1 on this, hence the range. But we can see here that if we have methyl orange, this is going just above 3 to just above 4, 3.1 to 4.4, and the indicator here has a pKa of 3.7, which is right smack bang in the middle of this value here. Okay, and then that is the region over which it will change color. So when we go to choose an indicator, we need to know where the equivalence point is to be able to choose an indicator where the equivalence point will sit in the middle of that range. Okay, so in this case, we wouldn't use phenolphthalein for a strong base weak acid titration. Sorry, we would use phenolphthalein for a strong base weak acid titration, where we wouldn't use methyl orange because its color change is outside the equivalence point. Okay, whereas phenolphthalein is going to change rapidly over this portion here. The methyl orange won't. But if we had an equivalence point that was down around 4.5, then we will see a sharper change in the equivalence point for methyl orange than phenolphthalein, because phenolphthalein is going to be changing over this much broader range here. So when we choose an indicator, we need to make sure that the pH range of the indicator will sit nicely at the equivalence point of the titration. So you can see here that we have a number of possible indicators for the strong base weak acid titration, in that bromothymol blue sits more around the equivalence point here, but phenolphthalein does sit on this very vertical region here, remembering that over the course of that vertical region it's going to change by less than 1 mil, usually about 0.1 of a mil. So for a volumetric analysis, we use acids and bases indicators to determine the equivalence points and hence know the concentration of the different acids and bases by titrating against standard solutions. And the selection of that indicator must be selected so that the color change, the PkIn of the indicator, is close to the equivalence point of the titration based on the salt hydrolysis and the acidic and basic nature of the salts that are left in the reaction. The next video is looking at buffers in detail and showing you how to do buffer calculations.